Okay, so hello everyone. I am Siddhartha Pramanik and I am a research scholar from the Department of Mathematics, IIT Kharagpur. So this is the live interaction session for the week 2 of the course Introduction to Rings and Fields. So before starting some problems, let me write down the keywords of the week 2. So in the second week, we have started with basically the definition of ring homomorphism. Then we have saw a certain subset of the domain of a ring homomorphism known as the kernel. Then we saw what do we mean by ideals. Then we have saw a special type of ideal known as principal ideal. So those ideals which are generated by a single element known as principal ideal. Okay. Then we have saw some operations on ideals such as intersections, sums, and products of ideals. And then we have saw nil radical of a ring. So I hope you all have gone through the lectures. Okay, so let's start with the first problem. In the lectures, we have saw that from the ring of integers z to z, how many ring homomorphisms are there, right? So from z to z, the only ring homomorphism. Okay, so from z to z, the only ring homomorphism is the identity map, right? So if we ask the same question instead of z, if we take the rational numbers, so find all the ring homomorphisms from the set of all the ring of all rational numbers to itself. Okay. So first recall that in our course we have assumed that all our rings. Uh, Let me write down it. So let me write down the assumptions which we are using in this course. So first assumption is here ring means always commutative ring with identities. Commutative ring with one and which is non-zero. So we are taking only non-zero rings. Second is all our subrings contains the identity contains one of the bigger ring. And third is the all ring homomorphisms, all ring homomorphism takes 1 to 1. So assuming this, we will do all our problems. So now, so what are the all ring homomorphisms from Q to itself? So any guesses? Anyone? Okay. So let let me write down the solution. So let phi from Q to Q be a ring homomorphism. Right. Then by definition, phi of 1 is equals to 1. So from this, what is phi of n for any natural number? So this is basically phi of 1 plus 1 up to n times. So this is n times. And since it is a ring homomorphism, so it is an additive function. So we can write like this. And this is basically 1 plus 1. Again, it is n times. So this is n. This is for all natural number. Now, what is the negative of this? Since it is additive, so phi of minus n should be, okay, let me, now it is also a group homomorphism under addition, right? So it takes 0 to 0. Phi of 0 is equals to 0. Now 0 can be written as phi of n minus n, right? For any natural number n. So phi of n minus phi of n is 0. Okay. So this is basically plus phi of minus n. So phi of minus n is minus phi of n, and which is minus n. So this is also for all natural numbers, right? So from these two, means this one and this one, we can write phi of a is equals to a for every integer. So now what about the fractions? So now if q belongs to a natural number, then we need to find phi of 1 by q. Okay, so let's try to see this. So phi of 1 goes to 1, right? So it can be written as phi of q by q, which is 1. Now this is basically phi of 1 by q plus 1 by q, and this is exactly q times. And since phi is additive, so this is q times phi of 1 by q, and this is equals to 1. So phi of 1 by q is exactly 1 by q. Now let's try to see what happens for any rational number. So now if P by Q belongs to Q, then we can assume P belongs to Z and Q belongs to natural number, right? By definition. So then phi of P by Q is equals to phi of 1 by Q plus 1 by Q. This is P times, and phi is additive, so this is phi of 1 by Q plus phi of 1 by Q. This is also P times. So this is exactly P times phi of 1 by Q. But phi of 1 by Q is 1 by Q. This is P by Q. And this is for every rational number. So phi of, let's say, A equals to A, or A belongs to Q. So that means phi is equals to identity on Q. So identity is the only ring homomorphism from Q to Q, which is same as Z. From Z to Z we have also only one ring homomorphism. So I hope this proof is clear. Okay, let's do another problem. So this is a true false type question. So does there exist a ring homomorphism from Q to Z? The other way we have already done. From Z to Q we already have one ring homomorphism, because one must be go to 1. But what about the other way? What about from Q to Z? Does there exist any ring homomorphism from Q to Z? Any guesses? If there exists a ring homomorphism, then what happens? So then 1 must go to 1, right? Then can you see what will happen if there exists a ring homomorphism? Okay, so let phi from Q to Z be a ring homomorphism. Okay, then by definition phi of 1 is equals to 1. Right. Now this can be written as phi of 1 by 2 plus 1 by 2, and this is exactly equals to 1. Now it is a ring homomorphism. It is also a group homomorphism under addition. So this is phi of 1 by 2 plus phi of 1 by 2, and this is 1. So this implies 2 times phi of 1 by 2, this is 1. That means phi of 1 by 2 should be 1 by 2. But this is not possible, right? Because this does not belongs to Z. So this is a contradiction. So there cannot exist any ring homomorphism from Q to Z. So this is false. Is it okay? Okay, so let's do a similar problem. So this is also true false type. So does there exist any ring homomorphism from the ring of real numbers to uh, ring of rational numbers? Try to do this. Now you should be able to do this. Try to think if there exists a homomorphism, then what happens? Yeah, anyone? Any answer? Or any guesses that it is true? First of all, it is not true or false. Sorry, it is just a question. Yes or no? Okay, no. Okay, can you say why? Or what is your ontoness fails? Do we need ontoness for ring homomorphism? Ring homomorphism need not be onto, right? Okay, then so if you try to do it in the similar manner, in a similar manner like the previous one, can you get something from that? Okay, let me write. So suppose there exists a ring homomorphism. So let F from R to Q be a ring homomorphism. Irrational numbers doesn't. What does that mean? Does not have images. Yeah, yeah, you are right. So let's try to see here. So if f is a ring homomorphism, then by definition f of 1 should be 1. So f of 2 must be 2. Now 2 can be written as root 2 times root 2, right? But it is a ring homomorphism, so it is multiplicative. So it is basically f of root 2 times f of root 2, and this is 2. So this means f of root 2 square is equals to 2. So f of root 2 must be plus minus root 2. But this does not belongs to Q, so it is a contradiction. So there cannot be any ring homomorphism from R to Q. Okay, so I hope all of you have understood. Now, what about the other way? What about from Q to R? Does there exist any ring homomorphism? Is there any shortcut for ring homomorphism from Zn to Zm? I think that is an assignment question, right? So I cannot say anything about that here, at least now. So what about ring homomorphism from Q to R? How many are there? If there exist any. Not asking for exact. So by definition, you can try to see how many are there from Zn to Zm. It should map 1 to 1, right? From that, you try to see by using the properties of a ring homomorphism or group homomorphism, because it has to be a group homomorphism also. Yeah, so how many ring homomorphism are there from Q to R? Anyone? From all at countable. No, no, no. So from Q to Q, how many are there? So from Q to Q, there exists only one, right? The identity map. So how we have done the proof? So one must go to one. Then we have saw all integers must go to integers. Then we have proved that all rational numbers maps to itself. So in a similar manner, here also all rational numbers. So if f from Q to R is a ring homomorphism, then phi of A is equals to A for all A belongs to Q by using the same method. So it is basically just the inclusion map from Q to R, right? So there exists only one homomorphism. So this is by same method in the first problem. Same method as we have done in the first problem. So only one ring homomorphism. Yeah. Okay. So this is very easy. Let's try to see somewhat complicated. So we have saw ring homomorphism from Z to Z, ring homomorphism from Q to Q. Now let's try to see ring homomorphism from R to R. So how many ring homomorphism are there from R to itself? Any guesses for this? Two. Okay. So what are the maps? 1 minus 1.
f of x is equal to 0x and f of x is equal to 1x.
Uh, First of all our ring homomorphisms maps 1 to 1, right? So it cannot be a zero map. So one ring homomorphism is the identity map. That is clear. So the
And the
question is,
second one will be minus x, f of x equal to minus.
no. In that case, f of 1 will be minus 1. So that violating our assumption. Okay, so we have assumed 1 must go to 1 in all ring homomorphisms. So you are saying this too. Why cannot be, why there does not exist any other homomorphism? Can you say? So I will be proving that if phi is a ring homomorphism from R to R, then that has to be the identity map. Okay, this proof is somewhat non-trivial. Let's try to see why. So let phi from R to R be a ring homomorphism. Okay, so then as we have done in the case of Z to Z, or more generally Q to Q, we have saw a rational number maps to itself because 1 goes to 1, right? So then f of, sorry, phi of 1 is 1 by definition. So from that you can conclude phi of a is equals to a for all a belongs to rational numbers by the same method. So this much we can say. So now let me say it as step 1. We will prove that phi is a increasing map. So increasing, okay, not say, let's not increasing. So if x is greater than 0, then we will prove phi of x is also greater than 0. So this is the step 1, and my goal is to prove that this phi is the identity map. Okay, so let x greater than 0 be a real number. Okay, now I will be using a result from analysis. So then there exists a real number r such that y square is equals to x. Okay, so this is you can find in an analysis book. So now phi of y square is equals to x. But phi is a ring homomorphism, so the left hand side is phi of y whole square. It is equals to x. But square means it is a positive number. So x is equals to phi of y whole square, and this must be positive. Sorry, it is phi of x. So phi of y square is equals to phi of x. I am applying phi to this equation. So phi of x is positive. So this proves the step 1. Now step 2. Now I will prove phi is an increasing map. Is an increasing map. So increasing means what? So that means if x less than y, then phi of x is also less than phi of y. We need to prove this. So let x less than y. Then that will imply y minus x is positive. Now by the first part, phi of y minus x is also positive. So that will imply phi of y minus phi of x, it is positive because phi is a ring homomorphism. So phi of y is greater than phi of x. This proves that phi is an increasing map. So we have proved the step 2. Now we will prove phi is identity. Phi is identity map on R. So we have already proved that phi maps all rational numbers to itself. So we need to prove only it for all irrational numbers. We can also prove it by contradiction. So suppose there exists a real number r which does not maps to itself, such that phi of x not equals to x. So I am assuming phi is not identity, then I will arrive at a contradiction. Then two things can happen, right? So what are those? Either phi of x is less than x, or phi of x is greater than x. In case 1, let's assume phi of x is less than x. Okay. Now we know that rational numbers are dense in real numbers. So this is also a result from analysis. So there exists a rational number such that phi of x less than r less than x. So this is because q is dense in r. So now r is less than x, right? And phi is increasing. So what can we say? Now r is less than x. So that will imply phi of r should be less than phi of x by step 2. where we have proved that phi is increasing map. But this is contradiction, right? Because but this is equals to r, as we have saw in the beginning. Phi of a is equals to a for all a belongs to q. So this implies phi of x less than r less than phi of x. This is a contradiction. Now this cannot happen. So what is the other possibility? So in case 2, phi of x would be greater than x. So in that case also we have a rational number. Let's say r belongs to q such that phi of x greater than r greater than x. Because of the same reason, q is densed in r. We can use the fact that phi is increasing. So r greater than x, that will imply phi of r is greater than phi of x. And since phi of r is a rational number, so this is r. So r greater than phi of x. And also r is less than phi of x. Again, we have a similar kind of contradiction. That will imply phi of x greater r greater phi of x. So this is a contradiction. So both of these two cases cannot happen. So phi of x cannot be greater than x. Phi of x cannot be less than x. So definitely we have phi of x equals to x. So phi of x equals to x for all x belongs to R. So phi is equal to the identity map on R. Is it okay? So only ring homomorphism from R to R is the identity map. Do you have any doubt in the proof of this? Okay. So now we have saw ring, ring homomorphism from Z to Z, that is identity. Q to Q, that is also identity. In fact, from R to R, that is also identity. Now let's take something bigger, from C to C. So C to C, actually there are more than one homomorphisms, but we will be restricted to somewhat special case. So it is problem number 6. Find all ring homomorphisms from C. Okay, ring homomorphisms. Let's say phi from C to C such that phi of R is subset of R. So I am assuming it takes all real numbers to itself. Then in that case, how many ring homomorphisms will be there from complex numbers to itself? So this is easier than the previous one. Try to think for few minutes. Yeah, anyone or any guess how many homomorphisms will be there? So the identity map is always there, and identity map also satisfies this condition: phi of R subset of R. So apart from that, anything else? Can you guess? Yes, any response or any answer? Okay, so let me write down the solution. So let phi from C to C be a ring homomorphism satisfies this condition such that phi of R must be subset of R. Now, using this condition, we can say that if we restrict phi to R, then that will also be a ring homomorphism. Then phi of R subset R will imply phi restricted to R from R to R is a ring homomorphism, right? So phi restricted to R is a ring homomorphism, and only ring homomorphism from R to itself is the identity map. So by the previous one, phi uh, restricted to R should be identity map on R, right? Up to this we can say, what does it mean? It means phi of A equals to A or all A belongs to R. So this condition, phi of R subset of R, forces phi of A equals to A for all A belongs to R. Now what about an arbitrary complex number? Now if A plus IB belongs to C, then A and B are real numbers, right? So then phi of A plus IB, we need to find this image, right? So phi is a ring homomorphism, so it is additive as well as multiplicative in the both. So it is phi of A plus phi of I times phi of B. But A and B are real numbers, so it is A plus phi of I times B. So if we want to find this image, it is we only need to find the image of I, right? So we only need to know what is image of I. Now, can you guess what will be the image of I? Uh, no, it need not be always I. There should be other possibilities. Others, any guesses? Use the fact that pi is a ring homomorphism. So uh, we all know that I is basically root minus 1, right? So that means I square is equals to minus 1. So we will use this fact. Now we know phi of minus 1 is minus 1. Now this is phi of I square equals to minus 1. But phi is multiplicative. So this is phi of I whole square equals to minus 1. So we have phi of I is equals to plus minus root minus 1. That means plus minus I. So it has basically two choices, I or minus I. So if phi of I is equals to I, then we have the identity map. Means phi of A plus IB equals to A plus IB. So phi is equals to identity map on C. And it is a ring homomorphism, we all know. Now if phi of I equals to minus I, then what happens? So then phi of A plus IB is just A minus IB, right? So phi of Z is actually Z bar conjugate for all Z belongs to C. So you can check that this map is also a ring homomorphism and it also satisfies this condition. Okay, so that part I am leaving to you. So phi of Z is equals to Z or Z bar. So we have only two ring homomorphisms in this case. Hence, there are only two ring homomorphisms in this. Is it okay? Did you got the proof? Restriction is okay. So I think you are saying if we remove this condition, then what happens? So if we remove this condition, then there can be other homomorphisms. Okay, so that part I want you to check. Let me put that as remark. So if we remove the condition phi of R is subset of R, then there can be other homomorphisms. Okay, so I want you to find some example for that. So let me write down that. Find some example. Please give the hint. Hint is that we try to think it now, then come back. Or you can ask in the next season also. Till then, think yourself. Because I have some other problems to do. So let me complete those things now. Okay, so I have done the ring homomorphism part. So now let's see some problems on ideals. is problem number 7. So which of the following, okay, let's let R be the ring of all continuous functions from R2 itself. Okay. Then which of the following are ideals of the ring R? Okay, so let me write down. So first one is f belongs to R, all those continuous functions, such that f of 1 equals to 0. Second one is f belongs to R such that f of 1 is equals to 1. Third one is f belongs to if all continuous functions such that f of 1 is 0 and f of 2 is also 0. Fourth one is all those continuous functions such that f of 1 is 1 and f of 2 is 0. So we have 4 sets, I1, I2, I3, I4. So which among these, which are ideals of the ring of all continuous functions? So try to think for few minutes. This is not difficult, so you can check it by definition. Try to see it by the definition of ideals. Try to check that the sets following the conditions of ideals or not. So you are saying B will be an ideal, and what about A, C, D, and why B is an ideal? So when a set I of a ring R is called ideal, so first of all, I has to be a subgroup under addition, and it should have the property that if R is in R and A is in I, then this product should be in I. So these two axioms should be satisfied. Or we can write it in a more friendly way. First axiom is if A be in I, then A minus B should be in I. And second one is R belongs to R, A belongs to I. That should imply RA belongs to I. The product should be in I. So these two conditions, which of the following sets are satisfying? Is any answers? So first try to check which of these are subgroups under addition. So to become subgroup, it must contains the zero element, right? And here in the ring of all continuous function, the zero element is the zero function. So from that, can you say something? Okay. So observe that the zero function does not belong to I2 and I4. Zero function means uh, it maps every element to zero. But in the second set, it one must go to one. It is not zero. And here also one must go to one. It is not zero. So zero function cannot be in I2 and I4. So I2 and I4 are not even subgroups under addition. They cannot be ideals. So this cannot be an ideal, this cannot be an ideal. Now what about A and C? First of all, are they subgroups under addition? If we take two function, does their difference? Yeah, okay. So in fact, they are ideals. So, I1 and I3 are ideals of R. So I will check for I1. So let F comma G belongs to I1, right? Then uh, by definition f of 1 is 0 and g of 1 is 0. Now what is f minus g of 1? So by definition it is f of 1 minus g of 1, and it is 0 minus 0, it is 0. So f minus g belongs to I. So it is subgroup under addition. Now if let's say h belongs to R, a continuous function, and f belongs to I1, then we need to check that this product HF belongs to I1 or not. So what is HF evaluated at 1? So this is H of 1 times F of 1. But F of 1 is 0. So this is H1 times 0. This is 0. So this product should also belongs to I1. So I1 is an ideal. Similarly, you can check that I3 is also an ideal. Okay, you just need to check that two axioms of in the definition of ideal. It's not difficult. I hope you have understood it. Okay, let's see one more. So in the lectures, we have saw the ideals in the ring Z, right? So every ideal in Z has the form mz, right? For some m. So every ideal of Z is principal ideal. It is generated by a single element, right? So recall that fact. So using that, if we take sum of ideals or product of ideals in Z, uh, how those ideals will look like. So, okay, let me write down. Recall that every ideal in Z of the form mz for some m greater equals to 0. So m is the generator of the ideal mz, right? Then find generators for the following ideals. First one is you can take 4z plus 10z. So this ideal is also of this form mz, right? So what is m in that case? And b you can take uh, intersection 4z intersection 10z, and c you can take the product 4z times. So in all three cases, what will be the generators of the ideals? So try to think yourself. So 2z for which one? So you are saying 2z for which of this? A, B or C? Okay, others? It the GCD for A? Ah, yes. Yes, you are correct. But we need to prove it. And for B and C? Okay, let me write down the solution for first one. So first one is 4z plus 10z. So let I equals to, so I is equals to 4z plus 10z. So I has the form of mz and we need to find the m. So now if a belongs to I, then it will imply a has the form some 2 times n, sorry, uh, some 4 times some n plus 10 times some m, right? By definition of sum of ideals for some nm belongs to z. Now it can be written as 2 times 2n plus 5n. So this is belongs to 2z. So I is subset of 2z. Now on the other hand, if b belongs to 2z, then b is equals to 2 times n, or let's say n prime for some n prime, right? But 2 is GCD of 4 and 10, right? So we can write it 4 times 2, okay, 4 times minus 2 plus 10 times 1 into n prime. This can be written as 4 times minus 2n prime plus 10 times n prime. So this element belongs to 4z plus 10z. So 2z subset of I. Now I subset of 2z and 2z subset of I. Thus I is equals to 2z. So I hope it is clear. So now can you guess any answer for B and C? Okay, B is the intersection, right? So let I is equals to 4z intersection 10z. So let okay, if B contains multiple of 10 and 4, so LCM. Yes, yes, you are correct. So if A belongs to I, then A belongs to 4z intersection 10z. Okay, 10z. So that will imply A can be written as 4 times n and A can be written as 10 times some m for some n and m integers. So that will imply 4 divides A and 10 divides A. From this we can say LCM of 4 and 10 divides A. Now what is LCM of 4 and 10? That is 20. 20 divides A. So this means A is equals to 20 times some D for some D. So this means A belongs to 20Z. So I is subset of 20Z. Now conversely, if you take any element from 20Z, then B is equals to 20 times some D prime, right? Now you can write this as 4 times uh, 5 D prime, and also you can write this as 10 times 2 D prime. Now this element belongs to 4Z and this element belongs to 10Z. So B belongs to 4Z intersection 10Z. So 20Z is subset of I. So we can conclude I is 20Z. Now what about C, the third one, the product? Okay. So again let I is the product 4Z times 10Z. So if A belongs to I, then what kind of element A is? Means how this is look like? Uh, exactly. It will be the product. Okay, so let's see the proof. So then A is basically summation, finite sum of some let's say xi times yi. I is equals to 1 to n, where xi will belongs to 4z and yi belongs to 10z, right? Because this is the definition of product. This is not just product, this is sum of products. So this we can write it as xi belongs to 4z, so it's multiples of 4, and yi belongs to 10z, so it is multiples of 10. So we can write it as 4, let's say xi prime and 10 yi prime, and I equals to 1 to n. So xi is equals to 4 xi prime, yi equals to 10 yi prime. So this is basically 40 xi prime yi prime, I equals to 1 to n. Now you can take 40 common. So this is basically uh, 40 times some d. So it belongs to 40z. So also in the other hand, if b belongs to 40z, then b is equals to 40 times some d prime, right? Now you can write this as 4 times 10 d prime. Now 4 belongs to 4z and 10 d prime belongs to 10z. So their product should be in 4z times 10z. So this side is easy. So 40z subset of I. So that means I equals to 40z. So from this we can generalize these things as one student is saying that the first one should be the GCD, second one should be the LCM, and this should be the product. So is it okay, the proofs? Do you have any doubt in the proofs? Okay, I hope you have understood the proofs. So let me write this as remark. So mz plus nz is basically GCD of m comma n times z. Mz intersection nz is LCM of m comma n times z, and this product is nothing but mn z. So you can do the proofs in the same way as we have done in the problems. Okay, so try to do it on your own. Okay, let's see next problem. So problem number 9. So consider the ring, the polynomial ring ZX. Okay. Now which of the following are ideals of ZX? So first one is set of all polynomials a0 plus an x power n belongs to R such that uh, 2 divides a0, means a0 is multiple of 2. Okay, let me put this as I1, and I2 is all those polynomials in ZX such that 2 does not divides a0, and C I3 all those polynomials such that either 2 divides a0 or 3 divides a0. So we have 3 sets. You need to check which of these are ideals. So you need to check this that 2 axioms of in the definition of ideals. So try to do this. B is not an ideal. Okay. So why can you say? 0 polynomial. Yeah. So 0 polynomial cannot be an I2. You are right. So B cannot be an ideal. Fine. Okay, what about the other options? So what about A and C? Addition may fail in uh, I don't think addition will fail in A. Okay, let me do it for the part A. So A in fact will be an ideal. So I1 is an ideal of R. Okay, let's see why. So if let us write as sorry, let fx equals to summation fix power I equals to 0 to n, and gx is summation gi x power I equals to 0 to m, are two elements are in I. So then 2 divides f0 and 2 divides g0, right? So that implies 2 must divides that difference also, right? So fx minus gx should be in I. Should be in I, and product is also clear. Also 2 divides f0 g0, so that will imply, okay, not in this case, yeah. So also if let's say h of x equals to summation hi x power I is equals to 0 to, let's say, r, belongs to any arbitrary polynomial, then 2 must divides f0 times h0, because it divides f0, so it divides f0 times h0. So definitely the product will belongs to I. Sorry, I1. I1. So I1 is an ideal. And as you are saying, B is not an ideal. That is correct, because 0 polynomial does not belong to I2. What about the third one? Did you understand this proof of A? I hope you understood. Yeah. So what about part C? Either 2 divides A naught or 3 divides A naught. So A is an ideal. So you just need to check two axioms: the subtraction and the product. Let me write down the B. B is not an ideal. I2 is not an ideal of R because 0 does not belongs to I2. So the third one, it is also not an ideal. Let's try to see why. I3 is not an ideal. In fact, it is not a subgroup. Okay, so let fx equals to some x plus 2 and gx is equals to some x plus 3. Then its zeroth coefficient is divisible by 2. So fx is in I3. Its zeroth coefficient is 3. So it is in I3. Then f comma g belongs to I3. But g minus f, which is 1, it does not belongs to I3. So it cannot be an ideal. Okay. So even in fact, can you so you have saw the definition of kernel of ring homomorphism, right? So can you identify this ideal as kernel of some ring homomorphism? Okay, let me put that. Put it as ring. Observe that I1 is the kernel of the ring homomorphism. Let's say phi from Zx. Let's say Z mod 2 Z defined by phi of f of x goes to f evaluated at 0, you take just bar or mod 2, you can say. F0 bar is basically F0 mod 2. Then check that kernel of phi is basically I1. Okay, I hope this is not difficult. So you just have to prove that two sets are equal. I think this will be useful, and you can generalize from this to get other ideals of ZX. Okay, fine. So we have saw ring homomorphisms. We have also saw ideals, principal ideals, personal ideals. Now let's do some problems on nil radicals. So this is problem number 10. So I hope you can recall the definition of nil radical. So it is just the set of all nilpotent elements, right? And this forms an ideal. So find the nil radicals of the following rings. So first one, let's say uh, Z mod 9Z. Second one, let's take Z mod 12Z. And third one, let's take C of R. So this is a notation for rings of continuous functions from R to R. So this is ring of continuous functions. Okay, characteristic. Characteristic is in the course. I think you will see it in the week 6 or 7 maybe. Week 7. Yeah. So rings of continuous functions. So what will be the nil radical of these rings? Means what are the nilpotent elements of Z mod 9Z? Can you quickly check? Of course, this ring is finitely many elements, only 9 elements. So you can try to check manually, but I will not suggest that. There are convenient ways of doing that. So anyway, can you guess something? Try to think it for a few minutes. Try to see for the first one. What will be the nil radical of Z mod 9Z? Yes, any guesses? Only 0. So you are saying in Z mod 9Z? Uh, Obviously no. See, in Z mod 9Z, if you take 3 bar, so what is 3 bar square? It is 9 bar. So it should be 0, right? So 3 bar is an important element. So its nil radical must be non-zero. Okay, let's see why. Uh, I will denote nil radical of Z mod 9Z. Okay, so I hope it is fine. Let x bar belongs to nil radical of Z mod 9Z. So then what happens? Then some power of this must be 0 bar by definition, or some n greater equals to 1. Now this means x power n should be belongs to this ideal. So an element is 0 in this quotient means x power n must be belongs to 9z. So x power n should be 9 times some d. So that means 9 must divides x power n. So that means 3 must divide x power n, but 3 is a prime number. So 3 must divides x. Right? Now if 3 divides x, then x is equal to 3 times some d prime. So here for some d. Here for some d prime. Now this will imply x bar is equals to 3 d prime bar. Now that will imply x bar must belongs to ideal generated by 3 bar. Okay, so from this we can say the nil radical of Z mod 9Z must be subset of ideal generated by 3 bar. Now let's try to see the other way. Now if y bar belongs to ideal generated by 3 bar, then y bar is 3 bar times some r bar. Now 3 bar is nilpotent. So that will imply, now you can recall that we have proved if x is nilpotent and R is an element, then Rx is also nilpotent. Now use that same fact. So what is y bar square? It is 3 bar times R bar whole square. So it is 3 bar square R bar square. But 3 bar square is 0. So this product should be 0. Y bar square is nilpotent. So y bar is nilpotent. So y bar must belongs to the nil radical of Z mod 9Z. So these two sets must be equal. So nil radical of Z mod 9Z must be ideal generated by 3 bar. I hope you have understood this proof. So if you have understood in the similar manner, can you say what is the nil radical of Z mod 12Z? Can you guess what is the nil radical of Z mod 12Z? Okay, so let's try to see. I think 2 bar. You are saying ideal generated by 2 bar. So is 2 an important element? I don't think it will be ideal generated by 2 bar. Okay, try to see it. So let x bar belongs to nil radical of Z mod 12Z. So then x bar power n is 0 bar by definition in the same manner. So x power n must belongs to 12Z. That will imply 12 divides x power n. Now what are the prime divisors of 12? It is 2 and 3, right? So 2 divides x power n and 3 divides x power n. Now 2 and 3 are primes. So 2 divides x and 3 divides x. 2, 3 are prime numbers. So this will imply x bar belongs to ideal generated by 2 bar and also x bar belongs to ideal generated by 3 bar in the same manner. So it belongs to these both ideals. So it must belongs to their intersection. 2 bar intersection 3 bar. Now can you say what is this intersection? Yes, you are right. So this is ideal generated by 6 bar. So nil radical of Z mod 12Z is ID subset of ideal generated by 6 bar. And 6 bar is nilpotent element, right? Because 6 bar square is 36, which is 0. So let's prove the other way also. It is easy. So if y bar belongs to 6 bar, then that will imply y bar is equal to 6 bar times some m bar. So y bar square 6 bar times m bar square, and this is 0. So y bar belongs to nil radical of Z mod 12Z. So these two sets must be equal. So nil radical of Z mod 12Z is ideal generated by 6 bar. Okay, I hope this is clear for you. So now can you guess what will be the nil radical of Z mod nz for any n? So let me put this as remark. So what will be the nil radical of Z mod nz? So from the proof, can you guess it? So what we have done here? We have taken an nilpotent element, then we have saw x power n belongs to 12z. So in the general case, it will be nz, or x power m belongs to mz. So m divides x power n. Then all prime divisors of 12 divides x power n. So in the general case, all prime divisors of n should divides x. So x bar should belongs to all those ideals which is generated by prime numbers and divides n. So it is actually is the intersection of all ideal p bar such that p is a prime divisor of n. Okay, so I think yes, this is the formula. So you can try to prove it in the same manner. There is no extra line in the proof. So you just write the proof on your own. Okay, so A and B. Now what about the third one? What is the nil radical of all continuous functions? So in the first lecture, means the first live session, I have proved that in this ring you have no non-zero nilpotent elements. So you can go back to that lecture and see. So I will just write down here nil radical of Cr is just 0. So you go back to the live season 1, you will find the proof that the ring of all continuous functions has no non-zero nilpotent elements. So I hope this is okay. Okay, so do you have any other doubts? So if you have no doubts, then we can wrap up today. So I have covered almost all the topics this week. I hope this is fine for you. Okay, so if you have no doubts, then let's stop this session here. Okay, then bye.